Alright, hello friends, let's talk about structs and classes today. This will be fun. So we'll learn about how they're like arranged in memory. We have technically already talked about structs, but it is time to revisit them. Okay, so here's stuff you know right now, and then we're going to go further. Alright, so if I make this struct foo, has 3 ints in it, yeah. The second I make an object of this struct foo type somewhere, if I do it in C, I have to say the word struct, remember? So if I make a struct foo somewhere in memory, like a local one, then I know some stuff about it, right? I know that, here it is in memory, right? Let's draw a picture of it. Here's a better picture of it. But the idea is it will take up 12 bytes, X, Y, and Z, right? Look like that, and then you can store stuff in it. You can store like 4, 5, 6, whatever you want to. Okay? We know it's going to take up 12 bytes total. Where do I want to put that? And then we know the offsets of everything as well, because every int is 4 bytes. Okay? So like, this will be 12 bytes. We know this. And then, yeah, if F started at address 100, then you'll see that the Y must start at address 104. The Z will start at address 108. They're all contiguous in memory, just like arrays. All right? So that's how that works, and each int takes up 4 bytes. That's how you know these things, okay? So these are the things we know right now. So like every int takes up 4 bytes. Let me write that slightly prettier. Every double takes up 8 bytes. And every char, that's just a single byte. Okay, so that's what we know so far. Do I want to do any of this yet in code? Not yet. Okay, your turn. So given that knowledge, here is a new struct, blah this time, alright? How many bytes do you think blah will take up, given what we just talked about on this previous slide? Alright, so give that a try. It makes enough sense, right? An int is 4 bytes, a char is 1 byte, another char is another byte, and then another int is 4 bytes. So let's go to code, and we can ask C or C++ to print this out. Struct example. We'll use C++ because we like C++. And so we can be like, hey C++, tell me, how big is blah? If I make something of the blah type, size of exists in C and C++, give me that size, please. And we're expecting to see, what, 8, 9, 10? 10 bytes? But we see 12. Whew. Alright, so this is why we're talking about structs again. There's something new going on. So let's figure this out. So the answer is E, surprisingly. Even though like the data itself takes up 10 bytes, the struct in memory, if we were to make one, C++ is going to have it be extra. It's going to hold extra space. It's going to take up 12 bytes total. Alright? So let's figure out why. The answer has to do with a concept called alignment. And I've said that word before, and now it's time to finally teach you what's going on. Alright, so the answer should be 10, but it's really 12, and here's why. Alright? It just so happens that it's much easier for the processor to read ints whenever they appear at addresses that are multiples of 4 bytes. So your computer, most computers these days, are really, really happy to read an int at address 112, and they're really, really unhappy to read an int at address 113. That's like, it takes more work for them to do that, if they can do it at all, okay? So the CPU prefers to read ints at addresses that are offsetted by 4 bytes, multiples of 4 bytes, okay? We call that 4-byte alignment, all right? So yeah, in most CPUs these days, there's a performance penalty to take a 4-byte chunk of stuff starting from an address that isn't a multiple of 4 bytes, which is called 4-byte aligned, all right? In fact, even in some processors, they just don't let you do that at all. So like you can't read from that address into an int. You can like read a byte from this address, but you can't read a whole int. That would be silly, okay? So yeah, that's what's going on here, and this is what it's going to look like in memory. Okay, deep down, we can confirm that, and I'll show that to you in a second. But here's what's going to what the memory will look like for this struct. The like add whatever its offset is, which will be a multiple of 4 bytes. You have the x, and then you have the 2 characters living here, and then you have empty space because we're waiting until like 8 bytes later, right? 8 bytes from the start, because that's another multiple of 4 to hold the y, the int y, okay? So that's really what's going on there, and we can kind of prove that. We can, let's see, is this worth it? Let's make a blobby. And be like, okay, hello, let's print out addresses now. Cout, what's the starting address of b, which will be the address of the x. Remember, this is the same as printing just the address of b's x, because they're the same place. The address of the whole thing is the address of its starting element. And then let's print the address of C1, the address of C2, and then the address of the y. And for a very weird reason, I can't just print the address of C1 and the address of C2, because the type, right, this will compute a char star, right, a pointer to a character. And then C++ is like, oh, you mean C string. Let me print a C string here for you. And no, we actually want the address. So let's convert it, let's cast it in a unhealthy way to something that it'll just print an address for us. So yeah, now I'm going to print out addresses. And here's what's going on here. So apparently this struct, as we made it in memory this time, it's different every time you run it, right? Different every time. So like, yes, it's 12 bytes long. It starts here at address blah 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 2d8, okay? Offset multiple of 4 bytes, yeah. And then the C1 happens 4 bytes later, so 8 plus 4 is C in hex land. Then D, right, to get C2, that's 1 byte later. And then the offset 6 and 7, which were the E and the F part, those are empty space. And then at E0, DD skips to E0, and that's where the Y begins. Okay, so it's exactly what's going on here for alignment purposes. That's pretty cool. Let's see, is there anything else I could tell you about this? Just for fun, like let's see what the, for some reason I did this last time, I can't remember why, but we're gonna look at it together anyway. So if I do like, hey, C++ emit assembly for this file, that'll make struct example.s, and we can kind of watch it do its thing. It's good to practice and see like what kind of assembly is going to get emitted for our files. So it's worth looking at anyway. And you see that there's some stuff to have to do with alignment, and we'll talk about that later. Maybe that's why I showed it to you. I showed it to the students last semester, but here you can kind of see like here it's printing 12 to cout. It's like it's figuring out most of these things automatically. But let's see if we can figure out where the blob B got made. It's probably getting made in stack memory. And so if we try to get the address of B, that's the next time we go to cout. So that's the 12 to cout. That's I can't even see where that's being called because it's hard to see, and I think it's like probably that. So there's, yeah, it's putting cout somewhere, and then it's printing stuff. Where's the easiest way to find that? So it's like it's going 4 bytes later. It's going 5 bytes later. That's where it's figuring out the offsets, I see. So apparently in the stack, SP plus 8 is where it begins. It's adding offsets. This is like the second character, for example. And then it's calling cout in a weird way. It's like the output operator. It's garbled right now. So we can ungarble this. We can unmangle this if we really wanted to. We can be like, C++, was it filt? And give this. It's like, what was that? Aha, so that was the output operator. So that makes sense. That's being called with cout and then what we're trying to output, which is this address. Okay. So yeah, that's what's going on there. You can see the 8 plus 8 to get to the address of y from this place in SP. And so it made this thing on the stack for us, apparently. When main subtracted from the stack, right here, it made room for our 12 bytes worth of stuff somewhere in there. Okay. So that's the goal. That's what's going on there. And it's worth reading this because it's the more you do, the better you get at it. There's some cool stuff that we haven't talked about, that it's calculating addresses of library things in an interesting way. You might want to look into that. So yeah, that's I think that's what I wanted to say for that. And yeah, alignment, very, very important. The CPU cares a whole lot about it. All right. So let us move on and talk about some cool assembly stuff that you might want to do one day. All right. I'll just write it down. We don't have to make new files to do it together. But here's some stuff you already know, right? When you say in your data section, I want some stuff, I want like a string, you can say, I just want a string itself with no null terminator, no C string, just characters, an array of characters essentially. Or you can say, I want a 0 terminated string of ASCII characters, which means C string, okay? So you know what both of these do. And here's kind of how they work. You make a label, and you're like, all right, at this label, at this address, when it gets assembled, I would like the string like hi to appear or something. And then that's going to make this in memory at that starting address given by the label. And then if you make ASCII Z, of course, that null terminates it. So that version of hi would look like this. It's got a third thing, really. The H character, the I character, and then the null terminator. So you know that already. Okay, here's some new things. Well, let's talk about some things that might make your life easier one day. There's one called equa, which is like short for equal. And what it does is it kind of works like this, and it makes a variable that's symbolic. It's not actually stored somewhere in like a register, it's just part of the file itself. It's, if you've seen this before, if you've done this in like a C or C++ file, you've done like a define foo to be 42 or something. This is just going to like copy and paste. Whenever it sees foo, it's going to replace it with 42. And that's what this is doing. Whenever it sees x, now it's going to replace it with 42. Okay, so that saves you typing. If you're going to use 42 a lot, you can call it something. It does not, though, appear in the data section. It's just going to get replaced. It's like it's going to do a find and replace every time you say something. Every time you say x. Okay, it gets pasted in, and then you can do like number sign x. That's kind of the idea. So you can say, let's set x equal to 42, and every time I ask about x, move into like, I don't know, W0 number sign x now. So it saves you some typing. To hold little constants like that. Move into W1 x again. Why not? Okay. So that's what you can do. We haven't really had a need for it, but it might be useful for you one day. And then if you want to create individual pieces of data that are a certain width, you know that you can make strings with ASCII, but if you like, I want a byte holding the number 42, you can do this. You can say dot byte something, okay? Dot byte 42, and that stores a single byte for you. You can also make an array of bytes and be like dot byte and then give a bunch of things. 1, 2, 3, 4, 5. So secretly, your ASCII, right? Your ASCII high is equivalent to you having made a byte array with the ASCII code values. Something like, I don't know. What's H and I? Let's find them. Lowercase h, it's got 104 and 105 there. So instead of this, you could have said dot byte 104, 105. Okay, you have options now. So that's a way to make an array of bytes. If you want to like hard code values, that's kind of nice to know, nice to have. And then we've shown you words before, right? Word is a 4-byte thing. This creates an int worth of 42, or an array of ints. You can do the commas as well. Okay, so those are 4-byte ints, and those are called words apparently. That's maybe also why it's a W register, right? For the 4-byte stuff. Interesting stuff to think about. So let's see, what could I tell you about this? So yeah, if you want to make an int in memory, and like the data section, like my int starts here, and it's a word holding 1,234. So that's going to take up 4 bytes to store this thing. That's what word means. Okay, you can also make arrays, so you can say in your data section, hey, I'd like an array of ints 1, 2, 3 or something. You can start that off in the data section like this, word 1, 2, 3. Okay, so that's useful to know. And then let's see, what else do I want to say here? Yeah. And then there's dot align, which I just showed you is being emitted in our assembly for interesting reasons. Usually you don't need it. I've never had you do it before, but sometimes it's useful. There's like dot align stuff. It's going to deal with memory alignment and like space and stuff out for you if you ever needed to. So here's what it does. Usually align, dot align is used in the text section, which is where your code goes. Oops, that's where your code goes. And you can see like dot text, it is by default, you don't really need to say it, but the compiler likes to put it in. So like all your code goes in the text section. All your other stuff goes in like the data section, okay? So if you say, if you say dot align and then give a number, it's going to make sure that the next thing that appears, right, the next thing that appears will be a multiple of 2 to the n bytes, okay? And so if you see like dot align 2, that's going to make sure everything is split by 4 bytes. It's aligned on a word boundary, okay? Does that make sense? Because it's going to align everything at multiples of 2 to the 2 bytes, all right? And that's why like you see that happening in the text section. If you say gcc-s or g++-s, you'll see this happening. That's what we did here to generate this. You'll see .align 2 to force. If it wasn't true before, it's making sure that all of these instructions, like this is the next real thing that's going to be placed in code, it's making sure that all these start on a multiple of 4 bytes, all right? Because every piece of code in ARM at least must start on a word boundary. It just won't run otherwise, all right? So that means it's going to start at a multiple of 4 bytes. Okay, so yeah, every instruction is also a word in length, if you want to use that term now. So a good example of why you might want this is if you put in your code section like a constant that's only a byte long, and like this was in the code section somewhere, like this was, like you had a branch somewhere, and like there was code in between, more code down here, like branch to foo, and like you were using this constant, and that was in your code section. You have to do align 2, like, I don't know what could go here, move into W142 or something, I don't know. You have to do align 2 here because look at what would happen, like this branch, this operation, like maybe it was code that started at address 100, then more code at 104, because they each take 4 bytes, right, pieces of code, and then you gave this constant in between code, all right, which you could technically do if you branched around it. What it would do is it would take up address 105 if that's where it was going, right? Address 105 to store a single byte, that new line thing. If you were to put more code, right after this without the dot align, like this move instruction appeared here, then it would start at address 106, which is not a multiple of 4, all right? And that would mess everything up. So you need to give some space, you need to pad it. With this dot align 2, it'll take care of like adding some extra space for you that makes sure like your next thing is going in address 108, shoving it there, all right? That's kind of the idea, and that's what you want, all right? That's what you'd like to have happen. And that's why you see dot align 2 omitted by the compiler, because it doesn't know any better sometimes, but it's also useful if you ever do something like this, all right? Because you have to make sure that all your code is aligned, and the assembler doesn't do it for you. It does not do it for you if you do something weird like this, okay? So yeah, that's dot align. With that in mind, now that you know about it, here's some code. Let's say it's in the data section, and let's say that foo, the address of foo, it starts at 20, address 20, okay? In that case, what will be the starting address of this Baz label? What's this address in memory? If foo is address 20, that's where it begins. All right, so I did align 4, go back to here, remember what that means, and then give it a try. All right, what's going on here? So like here's, if I know that address 20 is where foo starts, and foo takes up some memory, and then bar takes up some memory, and I say dot align something, and that might make some empty space, who knows how much, then where does Baz begin? What is this address right there? That's what I'm asking you. Okay, so if foo starts at address 20, what's going to happen? So foo is going to take up 3 bytes, right? Because it's got 3 things in it. So here's foo. Foo is taking up addresses 20, 21, and 22. That's easy enough. And then bar is a word, and it's just taking up the next space. So bar starts at address 23, and it's a word, so it's taking up 4 bytes total. Dun, dun, dun. So here is bar, taking up 4 bytes, doing its thing. So 23, 24, 25, 26, and then we say dot align 4, all right? And that's going to space out things so that the next thing you see starts at a multiple of how many bytes? 2 to the 4 bytes, which is 16, okay? One thing I think I forgot to say, I forgot to read it, is that once you have doubles involved, then you start needing like 8-byte alignment. So that's like align 3, okay? And things get a little even more spaced out than this. So that reminded me of that. Sorry, I forgot to say that. I wrote it down though. Let's see. So yeah, that's going to the next address of a multiple of 16 bytes. So, right, from 26 to what? What's the next multiple of 16 bytes? It's going to be 32, isn't it? 32, and that's where Baz will begin and store an int's worth of stuff. So it's going to take up 4 bytes starting at address 32. This is Baz's memory, 32, all the way to 33, 34, 35. Okay? So that means Baz starts at address 32, and that's how you figure it out. All right? I hope that makes sense. I guess the last little directive, assembly directive, that I want to teach you is .fill. And this is a way to make a big long array of stuff. It would make things easier for us. I know I can think of at least one example of something I wrote that would have been nicer to do like this, but we didn't have it at our fingertips just yet. So if you say .fill and give an amount, and then you give a value, and then you give how wide the thing is, because you're not saying .word or anything anymore, then what this does is it's going to make an array of 100 bytes, right? Because 1 byte, each holding the star character. All right, so this is equivalent to like saying, making the string a bunch of star characters, typing out 100 of them. Okay, so that's pretty nice. It'll do it for you. Okay, so that's the goal. Those don't actually look like stars, do they? The first one does. Let's make it pretty. There. So that would save you a lot of typing, wouldn't it? All right, so this is how it works. You say fill the number of bytes total, all right? So this is I could say 100 bytes because it was 101 there. Number of bytes total, the value you want to fill in there, and the size of each individual chunk, okay? So for example, if you wanted like 4 x's, this string with 4 x's, another way to do that would have been to say .fill, I want an array of 4 characters, so that's 4 bytes total, each having an x in them, and each chunk of things in my array is 1 byte long. So it's going to be 4 of these individual byte x's, all right? And so, yeah, it'll create an array of this many elements, num bytes over byte size elements, all set to this value. So if you wanted like a big long array of like 142s, and they were all ints, you'd say .fill, it would be 400 bytes total, right? Because it's 4 bytes, 100 4-byte things, each set to 42, 4 bytes each. So that's 142s. I hope that makes sense. All right, so that's useful. Now you know. Yeah, I think the next thing that I want to talk about is classes. Let's do C++. Let's figure out how it's getting converted to assembly, because this is disgusting. We need to learn more about it, right? Let's do it together. All right. So I'm going to ruin the magic. You're going to know exactly what happens when you write object-oriented code. How is it going and being converted into assembly? Because everything's being converted into assembly eventually. So let's figure this out. Let's make a simple counter class, like a class that just counts up one by one, and with like an int field and an increment method, and then we'll look at the assembly that gets created. All right, we'll figure this out together. So you can ask G++ to like do the -s, but the website godbolt.org is so much better. It's what people tend to use to see like how is the assembly going to get emitted. Okay, godbolt.org. And we can type in some code here for ourselves. So I have that. Let's replace it with like a class counter. All right, class counter, and what will we do in the counter class? We're going to make an int field. I don't know, we could make it private. Private int field, int count, I guess is what we'll call it, and then we'll have a public method that's just like an increment. So it's like void increment. Okay, something like that. I guess you can't really set the count. Let's make the count public too, just for fun. All right, so let's implement the increment method, of course. So let's do that. So this is the best place ever. It's going to demangle everything for us. All right, and so what does it mean to increment a counter object? Well, counter : increment. First of all, do I need to switch to a C++ compiler? We'll see in just a second. What does it need to do? It just needs to increment the count inside the counter. Okay, so that's kind of how it would work. And then I want to get rid of the O2. And let's look at it. Let's also make it like a main function, int main with like a return 0, and we'll make a counter object. Counter c.count starts at like 0 or something, and then we'll do c.increment. All right. So here's stuff. This is like the default level of optimization. No optimization at all. But do you see what's going on down here? Here is, first of all, we have like here's counter's increment, counter : increment. Looks like this. And then here's main calling counter increment. It's BLing to it. So the first thing that you need to notice, and hopefully somebody's told you this by now, is every method that you write is really just a function. It's just a secret function. And even though you write it like this, you have your object, object1 dot the blah method on it. This is really being converted by the compiler into a function call, where it's like, this was your class C or whatever, C : blah. It's like the blah method, and secretly, like the object is it's becoming the first argument. It's like the secret 0th argument. It's like the address of it actually is the secret 0th argument of this function, even though it's meant to be taking nothing. That's what it's being turned into. I hope that makes sense. All right. So that's how functions are being called. This is your this. That's how it knows about this, right? That's what this is. That's how it gets it, because every time it's secretly being called for, you're getting the address of your object, and that's how it's like going in and messing with that particular object's memory. Okay, so that's pretty fun to think about. That's how it knows to like mess with object 1 rather than some other object 2. Because really, it's just like a struct in there. Like maybe you have like a foo field or something. And object 1 holds 42, and then object 2 has its own, right? Has its own foo field. It's just like a struct, and it's at an offset somewhere. And so like you can go through this offset and mess with things. All right. So every method is just a function with a secret first parameter, and that is your this. All right. And this is always a pointer to your current object that you're messing with. Okay. So back to counter stuff. Let's figure this out together. So here in main, we make a counter object on the stack. Apparently, it's messing with the stack and it's subtracting from it to make space and all that. And then it's setting the count part of that counter, right? Because there's only one thing in the counter. It's just the int. So every counter object really is just 4 bytes. It made 4 bytes of memory in the stack somewhere for us. And that's all it means to be a counter. And then here it is setting it to 0. And this is actually the 0 register. Remember, back before there's a register that holds 0. It's storing that into the offset in the stack that holds the counter. C.count lives at apparently SP plus 24. And it's setting that to 0. That's the 0 register as an int, W0 register. And then it's calling increment here, C.increment, which is really a function call. It's BL to counter increment, and to like there's an argument, right? CX0, that's an argument to the increment function, and it's giving this, right? It's giving the address of the counter, which is at SP plus 24, like I said. So that's what's going in X0, and that's what counter.increment is seeing. And then we jump up here and we can use X0, right? We can use X0 for some weird reason. It's like loading and storing it to the stack for no good reason. It's unnecessary what it's doing here, but I think you can imagine what's going on. It is, it's taking it out. It is adding 1 eventually to that place at X0. So there it is. It's loading it into W0. That's the current count. It's adding 1 to it into a new register, and then it's storing it back into where it lives which was unnecessary. I don't know why it did that. It just really needed to store it back into the x0 place, which is where the counter was. That was the this. Okay, so yeah, and then it returns. That's pretty much what's going on. Can I do like an 01? Maybe will that clean this up for us? Unfortunately, no. Sadly, sorry. We got to keep it at 00. No optimization. Because technically, because I'm not printing anything, maybe if I print something, cout, c.count or something, then it'll keep it. But the optimizer noticed that I wasn't ever using this counter in any real way, and so it just like got rid of it. It compiled it away, which is hilarious. So let's see if this will keep it and then also make the code a little bit nicer. Much better. All right, cool. And so let's see, what are we doing here? Nope, it was smart enough to notice that it just needed to print 1. That's hilarious. Sorry. Never mind. Back to this. All right, so let's draw what's going on. All right, on the stack and all that. So it's like adding 1 to count. Here's like the relevant code, and then here's like the increment call. Everything after that was the cout that I guess I don't care about anymore. I tried. Compiler's too smart for us. All right, so let's kind of walk through this code and what's going on. So in main has made memory on the stack for my counter C. It's got a place to live. The counter C is only 4 bytes long because all it needs to hold is its count, which lives inside of it. Okay, so it lives apparently at SP plus 24, and that's where the count is being set to 0, just like that. All right, so that happened, and then we're calling c.increment. All right, so that's this line. If you hover over, you can see that like the red stuff. That's what's part of that call. So that address in x0 is the address of C. That's your this. And so we're saying, let me draw everything for that call in green. We are saying c.increment. All right, which is secretly going to be translated into counter : right? It's just a function call, : increment, with C as like the address of C as the 0th argument. All right, that's how that works. And so we jump up here and make a stack frame for counter : increment. All right, and then we have our this, right? We have our this parameter accessible to us that is a pointer to our C, and that's what it's going through. It's going through x0 in a weird way. It's like reading it out, adding back, adding 1 to the value that it read out, and it's storing that value back into x0, which is your this parameter. Okay, so that's what it's messing with. That's how it's doing it. I think that's what I wanted to say there. And yeah, so essentially when you say count plus plus inside of your increment implementation, that's really just being translated like into add 1 to the count member variable that was passed along in the this parameter, that secret 0th parameter. So this is really being translated into in like using that that pointer to get into that place. It's like this arrow count plus plus. That's essentially what's being translated into, because it's going through the this parameter and it's storing it back where it belongs. Okay, that's the idea. So you're passing a pointer. That thing lived in memory. Okay, so I hope that makes sense, and that's why that's going to work. That's why it's going to do the right thing. And so let me like zoom in on that idea of increment. Let's pretend we got called in a normal way. Let me up the optimization level, because at least the increment's still going to work. This is really what's going on in increment. So here's that. Forget about the rest. Like the main function is just return 0 because we're not actually using the counter. See, it's just too smart for us. But here's the essence of the increment function. This is its optimized form. All right, if we could just optimize that one. So we're getting called, right? And our this is sitting in x0 because that was our first parameter, our one and only. This is in x0, and then here's what it's doing. So x0 is a pointer to our counter, right? Our counter C from main. That's what's going on when we're running increment. Our counter C held a count, which holds 0 right now. And so what's going to happen is there. X0 is pointing to our counter. We are loading out into W1 the current value at X0, because all C is its own count. So this is equivalent, right, to just a box holding 0. That's all it is. It's 4 bytes. That's all you need to store a counter, right? That's all that's living inside of it is one int. So that's what it really looks like. It's just a 0 there at that address in X0. So we're loading that into W1. We're incrementing it, add, right, making it 1, and then we're storing that back. Store this back here, or really just here, right? Store it back into X0, this parameter. So that's why we see the 1 there, or you can think of it like the 1 there, okay? That's what's happening. That's what increment does. That's how classes work. Isn't that cool? So yeah, I think that's what I wanted to show you. So let's make now a like constructors and destructors. We'll watch it work. So let's make a constructor, a destructor. We already have our C object, and then we'll see how the assembly looks once we do such a thing. All right, back to 0 optimization level. So let's make a constructor and a destructor for counters. Counter, and then I can actually make the count private now. So there's that one and that one. Let's implement them in some normal way. So here they exist now. Oops. Unindent, unindent. A good constructor for a counter should set the count to 0. A destructor, what should it do? Oh, sorry, it's counter : : counter, of course. Counter : : tilde counter. And then the destructor, I have nothing good for it to do. Like, we can set the count to 42 right before it goes away or something. I don't know. Unnecessary stuff. But yeah, let's take a look and see how it's doing things. So here I am making a counter C. Dun, dun, dun. It's implicitly calling the constructor, so I don't actually have to do that anymore. And then it's incrementing itself. All right. So what's the best way to do this? Yeah, let's see what's happening in main. All right. So we make our counter C. The assembly that's being emitted, let me make this whiter, the assembly that we're seeing here, if I make this over here, what's corresponding to this, you can see that we've made space on the stack, of course, like that we've subtracted from the stack. It's still 4 bytes for every counter. And then we're also calling the constructor. You see the constructor being called there in red. Let me scroll up. So it's passing along, again, it's the address of the counter, right? The address of the counter is being given to the constructor because it needs to set member variables. It needs to know where that particular counter's count member variable lives. So there it is, adding it and BLing to counter. And then it's doing the same thing. Go into X0, call increment, because that's the increment method call. And then whenever we're ready to go away, whenever we hit the end of main, we have to destruct our counter. You see that that's being implicitly called for us. Again, it's given the address of the counter, and then it's BLing to the destructor. All right. So yeah, if you're ever going to do assembly class stuff, you have to call the destructor yourself. Does that make sense? So that's why C++ is nice to us. Dun dun dun. So yeah, let's look at the assembly that is generated. Let's look at the optimized assembly for these guys. It's easier to look at. So for example, the constructor is just like, all right, we're given in our this parameter, the address, X0 is the address of where the counter started, and that was where the count was. That's the only thing that's in that memory. So just store 0, this is the 0 register, store 0 into X0, and then you're done. The destructor is smart enough to know, we're never using the member variable again, so it just got optimized away. If I go back to O0 for the destructor, you can see that it is going to go into X0 and set the value to 42 for fun. So yeah, that's kind of how that works, and it's going to be called for you, unless if you're using C++ at least, it'll be called for you one way or another if you remember to clean up after yourself. And then yeah, just methods in general. They're all going to get turned into function calls with your this parameter being the secret 0th thing. If you have other things, let's make a reset method. So we can say c.reset. The counters count to 42 or something. then this will again be translated into a call, but now we actually have two parameters. This will turn into like a counter reset with the address of C as your this parameter, and then also like 42. So this is going to go still in x0, and this is an int, so it'll go in w1. Okay? So yeah, the first argument is always going to be this. All right, let me prove that to you. Let's make a reset method. Int new count or something. That can be it. So its job is to reset our current count to whatever the new count is that we passed along. And we'll say that here, c.reset42. Let's watch that work. So here is the call to it. We're calling it with reset. So again, x0 is the address of our object, w1 is the int, because that's now the second parameter, not the first anymore. And then we bl counter reset, and reset looks like this. If we optimized it, let's look at the optimized form, because it's just messing with the stack for no good reason. You can see that the reset just takes whatever was in w1, shoves it into the address at x0, which makes a lot of sense, because this is the start of that count. Take that new int, put it as your count, essentially. Okay, so yeah, that's how it works, and yeah, everybody's going through this essentially. It's always using the address. It's always how it accesses like your particular member variable, because you could have also had a counter D, and you need to know, like, am I calling this method on a C or on D right now? They're different places, and so that's why you pass along the address of the object you want to mess with. Okay. So yeah, I think that was everything that I wanted to talk about for classes. Now you know about the magic. If you ever had to call class methods, though, in assembly, you have to remember, like, you have to call the constructor, you have to call the destructor yourself if you're doing assembly. It's a little disgusting, I know, but that's what C++ is good for. It's doing all this stuff for you to hopefully make your life easier as a programmer. But at the end of the day, the compiler needs to know how to do this. It's emitting these calls to these constructors and destructors for you, which is cool. All right. So yeah, I think the last thing before we go is I want to introduce your next homework 2. So pay attention to that due date on Canvas. But here's what you'll be doing. You'll turn in this file with your answers. So you are going to be working with floating point numbers. So everything IEEE 754 32-bit floats, which I'll call F32s. Remember that you got your sign bit, you got your 8-bit exponent, biased by 127, so you got to like add 127. So go back to our slides from before for that. And then you got your 23-bit mantissa, and this will walk you through, like, you got a bunch of problems where you're making assembly stuff, all right? Or not assembly stuff, you're making floats with, in just like bit and byte form, okay? So remember that decimal places look like this, like this is 2 plus 1 plus this is 2 to the negative 1, 2 to the negative 2, so a half and a fourth. This is the binary form of 3.75, all right? So yeah, you're just gonna do all these problems. So like here's convert 4.0 to 32-bit float. It's like fill in the sign bit, convert 4 to binary, shift it so that it's in binary scientific notation, give me the mantissa after you drop that leading 1, figure out how many times you shifted, because you're going to have to bias that, and that will be your exponent. Give me the 8 bits of that, and then give me the 32-bit number, the sign bit, the exponent, the mantissa. So you're making that, all right? And then do negative 5.5. So again, like convert just the positive version to binary, you know what the sign bit needs to be, right? And then figure out, like, after you've done binary scientific notation, how many times did you shift it, so that you can do it all over again. So convert that one, 0.0625, negative 13.375, figure it out, right? You'll make it work. I believe in you. And then the last problem is just like write down any kind of nan, any kind of not a number, and we can go back to the slides and figure out what are the different ways. You have many options, right, to output a not a number, a nan. So that's your homework too. Yell at me if you have any questions about it, and I'll see you in the next video.